He has published more than 550 research articles and 14 book chapters, and holds more than 130 patents. He received the ACS Award for the creative invention, the Giulio Natta Gold Medal of Italian Chemical Society, the Team ID Texas Printed Electronics Europe Award, and the Corporate Plastic Award. He is a fellow of the European Academy of Sciences, National Academy of Inventor, MRS, AAAS, PMSE, Kavli, and RSC. Today, Professor Anthony Facchetti will give us a talk about the unconventional semiconductor materials, processes, and devices. Let's welcome Professor Anthony Facchetti, please. Thank you.
Okay, good. Okay, thank you again for the invitation, Wenping and all the team there in Tianjin. Congratulations about the new journal. And today I'm going to try to talk about some of the work we've done on developing unconventional materials and processes. This is a collaboration between Northwestern, Facchetti, and other collaborators that I'm going to elongate during my presentation. I'm going to try to talk about 4 topics. One is about describing new way to photolithographic patterning organic semiconductors. This is very relevant for producing organic transistors. Then I'm going to try to talk about a new way to enable plasticity and elasticity in organic semiconductor by molecular design, as well as new topological way to define films. Third, about some of the work we've done on porous and hybrid semiconductor morphology for electrolyte transistors. And then if I have a little time, I'm going to talk about a very recent work related to doping and doping of organic semiconductors. So the motivation of the work, as you probably know, my team and the work we've done at Facchetti and with Collaborators has been to develop materials and components and devices in the area of flexible printed electronics, transparent electronics, energy harvesting, storage, as well as bioelectronics a little bit. And the idea is to go from devices which are rigid, heavy, processed at high temperature, bulky, to devices instead which are more light, flexible, processed at lower temperature, compatible with plastic and fabrics. And these are quite considerable industry. And here, this is the size of this industry a couple of years ago. If you look at the technological transition in terms of the materials, you go from material which are mostly inorganic, processes high temperature, very stable, very durable, very reliable, typically hard and rigid, to materials instead which are mostly organic, lower performance, usually less stable, particularly to processes which are typical in the semiconductor industry. And this is one of the key motivation of the talk I'm going to today. Usually more soluble material, process at lower temperature. And the common idea is these materials are more soft, flexible, and stretchable, although this is not the case in many cases. And the device I'm going to mostly talk about is this thin film transistor. Is a device where you control the current in the semiconducting layer by applying two potential between the two conductors, source and drain, and the conductor here at the bottom, which is the gate electrode. And here you change the carrier density by using this gate voltage. And the materials are needed are the conductors, the semiconductor, the dielectric, and there is also passive material at the interface. And we've done quite a lot of work with collaborators, and these are some of the highlighted in red, the collaborators, in developing materials as well as processing and study charge transport at the interface between the semiconductor and the dielectric. Most of the work we have done has been in the chemistry. I'm going to talk about very little about chemistry today, but I just want to give you a flavor for those of you who are less expert in this field. In the semiconductor, there is electron transporting materials which transport electrons, and there is hole transporting material which transport positive carrier holes. And these are examples of small molecule and polymers we design and we published in the past for N-type, and here an example of P-type small molecule and polymers we developed. And just to get the introduction going, this is a polymer, it's a very old polymer we published like 15 years ago. It's an electron transporting material. And this has been widely used in transistors as well as in other TFT and other type of electronic architectures. And the polymer can be processed by spin coating, but also by printing. This is an example of inkjet printing. This is an example of gravure printed circuit done again with collaborators. It's a polymer which is a good electron transporter material. The field effect mobility in a TFT of this type of structure is about 0.2. For those of you who are organic chemists, this is not an ideal polymer because there is a torsion here, which is quite significant. It's on the order between 30 and 40 degrees. This has been measured experimentally. So one of the things we have done is to release this torsion to make the polymer flat. And from the molecular design, making it flat, it should make a better polymer. And one way we did it to make it flat is by removing 2 carbonyls. And if you remove these 2 carbonyls here, you end up with this polymer. If you remove these 2 carbonyls here, you end up with the second polymer. And this polymer is actually more twisted than the first polymer and is an inactive polymer. Instead, the second polymer, which is much more flat, when it's measured in the same condition, the mobility is larger. And then if you use the right comonomer, you can increase the mobility even to a greater extent. Okay, so from chemistry, there's still things that can be done to improve the performance of these materials. The polymer has been, as I told you, has been processed using many methodology, going from inkjet printing, gravure printing, flexo printing, brush printing, and also another technique we have been used is bar coating, where the technique can align the polymer chain in the direction of charge transport or perpendicular to the charge transport. And here you can get, this is the field effect mobility. When you process perpendicular and parallel to the charge transport, you see here large variation in mobility. This is called charge transport anisotropy, and also very large mobility that can be achieved. So the message I want you to convey is we can do chemistry and we can do process and we can change the performance considerably. And this is very good for transistors, for organic transistors. But in reality, the competitor in terms of technology is amorphous silicon, okay? Amorphous silicon, the field effect mobility is between around 4.5 centimeters squared per volt second. And I show you mobility going from 0.2 to 6. But OTFT are produced in fab line, which involve a chemical vapor deposition and sputtering. These are produced on very large glasses. This is an example of a Gen 10 glass. And the process which are employed in this type of production are only spin coating and slot die coating, okay? So the OTFT to be successful has to be enter the production of fab line using these type of processes. And so that you have a flavor of how the TFT is built in real line, you start from your substrate and then it is a buffer is placed. And then you put your electrical contact, you put the semiconductor, the dielectric, the gate, the passivation, and then you end up with delaminating the TFT array and integrating the front plane. But what is very key here is that all the processes involve, as I said, spin coating or slot die coating, and they involve photolithography. There is no printing in production of TFTs at the moment. So it is essential to use a photolithography to pattern the semiconductor. And there is several methodologies to do that, but we used a new method which involved to take a polymer, which can be a P-type or N-type, and then blend it with a photocurable resist, which can be based on molecular epoxy, epoxide, or photocurable 2+2 cycle addition chemistry. This is not so important. But the important is we can mix the polymer with the photocurable additive. We get a blend. The blend is spin coated on the substrate of interest, and then is UV cured. And then you need to develop to create your photoresist, your photopatterned semiconductor area. And then you can also soak this photo pattern area to a greater extent. So basically, we can get a number of films which are at different stages of the process. This is an example of the patterning on a 4-inch silicon wafer, and you see this here is the image of the world. You can see well definition of all the feature, and the green area is the semiconductor blend after curing and patterning. And you can see here the very nice definition. So there is a key question we wanted to answer. Obviously, the question is, are these blend after curing and developing remain semiconductors, and how robust are these film to additional processes? And this is an example of a DPP, which is this first polymer, and SU8, the second photoadditive blend. And this is the film morphology after spin coating, before curing, after developing, and after soaking. And you see here, the morphology remains very, very robust, very little variation in terms of topology. And these are some of the X-ray of the film. Again, here are the film, the uncured, cure, develop, and soak. And you can see here they retain the crystallinity of the DPP polymer. So basically tell you that after curing of the additive, the film remains very, very robust, and somehow the semiconductor is embedded into the cross-link matrix and remains very, very textured. And we can achieve a resolution which is on the order of 1 micron, which is more than enough to make back planes. In terms of charge transfer, we made the devices. I don't have time to go into detail, but this is an example of IV curve for the polymer. If it's not patterned, you have a lot of leakage current and a very poor on-off ratio. If it is patterned, you see a much, the leakage is negligible because there is no parasitic current. You have a nice on-off ratio. There is a little of hysteresis in the case of the DPP polymer. If you photo pattern instead of the N2200, the N-type polymer, here there is really no hysteresis, but these are quite well-behaving devices. So very good devices, which are very, very robust. We can take this TFT, immerse it into chloroform for 24 hours, and the device remains functional. You degrade in mobility, but I mean, you don't really need to put a TFT array into chloroform for 24 hours. So it just gives you a flavor of the robustness. Also, we check the thermal stability, and when the semiconductor is cured, the thermal stability is much better. And the bias stress is also quite good. And the process is also compatible with a very soft and flexible substrate. So we can pattern the P-type blend, the N-type blend, and check the bending, make inverters. The gain is not exceptional, is on the order of 12, but this is a sort of proof of concept. So this is basically a different way to being able to photo pattern the semiconductor, which is compatible with fab lines. Let me now switch to a slightly different topic and talk a little bit about mechanical properties of the organic semiconductor. And the common thoughts, what we hope as organic chemists, is that organic semiconductors are very soft. So they are not only elastic, but also they are plastic as well. And this is the hope, but as a matter of fact, this is not typical the case, particularly for very high performance semiconductors. These are typically, they don't exhibit any plastic, but they don't exhibit any elastic, but neither any plastic deformation. The plastic deformation is very small. Also, what is very important is we talk a lot about flexibility and stretchability, but the requirements are very, very different than you simply bend the semiconductor once or the device once, and instead you flex it many times or you stretch. So the demand is quite different in terms of mechanical compliance. just to give you a flavor, this table shows some of the Young modulus and the elongation at break. So this is the crack onset for some example of semiconducting polymers and small molecules. And these are the numbers. So you want to have a Young modulus, which is very, very small, and the elongation at break, which is very, very large, okay? And if you compare this number with typical electronic inorganic materials, the Young modulus indeed is much smaller than this, and the elongation at break is larger. But if you compare the number with the real elastomers, like PDMS or SEBs, these are large and these are small. So what the community has done is to improve these numbers by blending, and you can blend P3HT with different type of PDMS, put in an ionic liquid, put in some elastomers, and you see here that there is a depression of the Young modulus and an increase in the elongation at break, which is a very successful strategy, works very well with polymer. And in many cases, this process also improved the performance of the semiconductor, so it's not always deleterious. However, this type of approach does not work with small molecule, and the reason is if you throw in polymers, you have a phase separation, so the small molecule does not get plasticized. So we wanted to demonstrate this is instead it is possible, and we took as an example this small molecule, which we know it is a polycrystalline small molecules. And if you bend this film of this small molecule on a PN or PET substrate, you bend it, it forms crack very, very soon. So it is not an elastic material at all. It's a good N-type semiconductor, however. So how can we try to plasticize this film? And the way we did it is to design a polymer which has a polymeric backbone, but then it has end unit which has a sort of molecular recognition with the small molecule. And our hope was that this additive will segregate the grain boundaries of the film and somehow plasticize them. So what we did is to prove the concept, we prepare film with the small molecule, adding this polymer in different content, going from 0, so only the small molecule, 2.5, 5, and 10%. And then we started bending this film. And you see here that if you don't add any polymer, the film crack. You add about 2.5%, it's still cracking a little bit. But after you put about 5%, you don't see formation of any crack upon bending. So 5% is a sort of optimal amount where there is no phase separation of the polymer and the film does not crack. And if we do a mixture of N2200, so the polymer without the red components, and you bend it and you add it at 5%, it's still cracking. So there is a huge difference between adding this polymer versus adding the polymer without the molecular recognition and the unit. So you need those. And this translates to devices which, when you bend it, so just look at these two plots. So the black plot, if you bend these devices multiple times, it cracks and then it continues to degrade the performance. Instead, if you add about 5% of the additive, at the beginning, there is some cracks forming, probably something we don't see here. So probably there is some region of, and maybe you actually see here a little crack here. So there is a small degradation at the beginning, but then after this first crack form, there is no additional crack propagating because there is plasticization of the grain boundaries. And we indeed, using different technique by mapping by elements, this is a mapping of a grain boundary. And in the grain boundaries, you see a lot of sulfur, and sulfur, it only belongs to the polymer. So indeed, this polymer likes to phase segregate the grain boundaries. So it's a sort of different strategy to plasticize them. And of course, if we add N2200 to this transistor at 5%, it doesn't plasticize the film, so the device degrades. Let me go back actually to the plastic properties of N200, and we can make film on elastomers and stretch them and to measure some of the properties. And the film is not a very elastic film. You know, you see formation of crack here in the dark region. The Young modulus of this polymer is about 1.5, and the elongation at break is about between 1 and 2%. So it has it's basically not a plastic polymer, a very small, very small plastic and elastic deformations. So how can we plasticize it? What we did it, and this is a work we haven't published yet, but I want to repeat some of the concept, is sort of learn from comparing polyacetylene, which is a fully pi conjugated polymer, with polyethylene, which is a pi deconjugated. And you see here, when you have these double bonds, the Young modulus becomes large, and the elongation at break becomes lower compared to the corresponding plastic polyethylene here. So the idea is we can take a polymer and throw in the red components, which has a deconjugated unit, which looks like polyethylene. And the hope is to depress the Young modulus. And this is in fact what we see. Just look at this plot here. The blue component gives you the Young modulus of this polymer, the 100% conjugated. And the Young modulus is about 2.2. And when you start throwing in the red component, the Young modulus first decreases quite a lot, and then it decreases, but to a much less extent. We are still trying to study this, but the polymer becomes softer. And if you make transistor, then if you make the transistor with the fully conjugated, only this component, the mobility decreases very, very fast. And if you make transistor with only the red component, the mobility decreases much less. And in between, you are in between in terms of performance. So basically, by deconjugating the polymer backbone, you can pick up in the elastic behavior. Another approach we follow to try to improve the elasticity is by learning from work done on inorganic, and particularly on gold. If you take a film of gold and you stretch it, it cracks, right? But if you take a gold serpentine type of architecture, or gold having resin areas, and you stretch it, you have a different way to dissipate the energy, the mechanical energy. So it's a way using a morphology to make the structure more elastic. So the question is, can we embed this type of morphology into organic semiconductors and in a very effective manner? And one way to create this type of morphology is by using what is called a breadth figure methods, which consists to spin coat the organic semiconductor film in an environment containing water, so a very high water relative humidity. And the process is such a way that you have water condensation during the spin coating, and these water droplets create the cavity, which creates the porous morphology, okay? And by changing the water pressure, by changing the solvent, you can tune the porosity dimensions quite accurately. This is an example where we can control the topology of the dimension very, very accurately. We don't have to. But having this porosity, then we can make devices where having porosity, you can enhance properties. For example, if you want to sense an analyte, you want to have a semiconductor which has a lot of surface area, and having porosity, you can enhance the sensitivity. Or for electrochemical transistor, having porosity, you can penetrate the ion more efficiently, you get higher currents. Or you want to dope it, you can dope more efficiently. So porosity is important to enhance certain properties, but also is important to, I don't know if this is going to start, yes, to create a film which are much more stretchable. This is a work is under revision. It's really a way to embed mechanical flexibility into a film structure. Another thing we have done using porosity is to use them for electrochemical transistors. And in these devices, in terms of architecture, is very similar to a top gate thin film transistors. But here you have an electrolyte. And the way the device works is that by applying the gate bias, you have intercalation you have redox chemistry into your semiconductor. So the semiconductor gets oxidized and reduced electrochemically. It's not only an electronic process. And then to achieve efficient redox chemistry, the ion of the electrolyte has to penetrate. So you have to have an efficient penetration of ions into your semiconductor. So the question we ask ourselves is, if we make porous film of different semiconductors versus the dense film, is this important for organic electrochemical transistor? Is always important or not? This is basically the question we ask ourselves. So to address this point, so we use 3 different polymers, and for all of these polymers, we have been able to create conditions to achieve film which have porosity, and the films are also semi-crystalline. These 2 films are much more textured compared to this third film. And then we made the devices, okay? Again, I want to remind you, the question we ask ourselves, is porosity important or not? So we made devices using the porous film and the dense film. So we have 6 films, 6 type of devices, because we have 3 polymers. And then, as I said, this polymer, this is much more hydrophobic polymer. This is much more hydrophilic. These 2 polymers are much more textured. Instead, this one is much less textured. And then we use 3 types of electrolyte. KCl, which is a very hard, where the chloride is a very hard anion, so it is intercalate very, very poorly. Instead, the other 2 electrolyte, they intercalate much more efficiently, okay? And these are some of the results. There is a lot of data, I don't have time to discuss them, but this is the transconductance, basically, and you want to have it as large as possible. And what you see here is that this is the transconductance for when we use the chloride, so it's poorly intercalating, and this is when we use the other one of the other 2 is the same for either the other electrolyte when it's very intercalating. And what you see here is, first of all, the porous structure, which are these points here. I'm sorry, I should have put different colors, that are always larger compared to the dense films, which are this one. So it means indeed the porosity always enhance the transconductance to a certain extent. But you see here when the electrolyte is poorly intercalating, the variation is very, very large, okay, for the hydrophobic polymers, okay? Instead, when you use the highly intercalating electrolyte, the variation for the hydrophobic is much less. Instead, for the hydrophilic, the variation is insensitive to the quality of the electrolyte. This type of process is also reflected in the switching time of the devices. So it's, there is a big variation when you use a KCl. There is almost negligible variation when you use the highly intercalating anion. So to summarize it, because there is a lot of data, I don't have a lot of time, is porosity important? So typically you can enhance the transconductance in all the cases. However, having porosity is very, very important if your semiconducting polymers it is hydrophobic and very, very textured. So and if you have an intercalating electrolyte which is poorly intercalating. However, if you have a very hydrophilic semiconducting polymers, it doesn't really matter if you have porosity. No matter what, this ion can intercalate. So having porosity, you get a little gain, but it's not as much as you would have having a much more hydrophobic polymer. So porosity can be important or not, depending really on the combination of your semiconductor and the electrolyte. Let's see if it's working. Okay. Now let me go to the third part of my talk, which is a little bit talking about mixing organic and inorganic. And we have done a little work on using metal oxide semiconductor for TFT, particularly for thin film transistors. And metal oxide are great semiconducting material because they're optically transparent. They very large electron mobility, also in the amorphous states. And you can prepare this film from solution. Are inorganic, that they can be processed from precursor, which are from solutions. And we have shown that we can prepare metal oxide films using a technique which is called combustion synthesis, which allows to produce metal oxide film, which are very, very dense at low temperature. This is not so important. What is important is that by using combustion synthesis, we made many different type of TFT process at very different temperature in many different ways. What is very, very important, and I want you to remind you, is that metal oxide are great for electron transporting material. Instead of organic, the best organic are typically hole transporting material. So the question we ask ourselves, can we combine them, particularly if you want to make electrolygated circuits. If you look at the literature, particularly for N-type electrochemical transistor, this is still very lacking. So our idea was to use electrolygated and use a P-type organic functioning as an organic electrochemical transistor. So I want to remind you, electrochemical transistor means the ions have to penetrate into the semiconductor. And then instead I use an N-type indium gallium zinc oxide metal oxide as a function instead as an electrical double layer TFT. So here you have only ions which stop at the interface with your semiconductor, and you have a formation of an electrical double layer. So the two components of these circuits are using the same electrolyte material, but their way of function is very, very different. So we made this is the schematic basically of the unit of the inverter unit. So as a P-type, we use an organic, which is porous, and is going to function as electrochemical transistor. And then we use an indium gallium zinc oxide, which is very dense, and is going to function as an electrical double layer transistor. And by changing the porosity of the P-type, and by changing the indium gallium zinc atomic ratio, we can achieve in such TFT, which are quite balanced in terms of current and in terms of turn-on voltage. And when you combine these two, you can make inverters where the gain start becoming very significant because of the very low voltage. You know, the power is very low, and we made a number of the other different type of circuits. And this can, particularly this inverter, can be used to amplify signal. And this is an example of amplifying simply the eye movement, which is associated to ultra low voltage variation if you don't amplify to a variation which is on the order of the millivolts, which is tens of millivolts, which allows efficient amplification. So basically, the message is we can indeed mix and match organic and inorganic also for electrolygated type of circuits. Very briefly, I want to talk about the last topic, which is about the doping of the organic semiconductors. And this is a sort of an important process because we can basically tune the carrier density in a material, so changing the conductivity by using a process which consists in transferring charges. And this is an example of a direct molecular doping of the N-type. I don't know why this is happening. An N-type using this amine. So this amine can directly transfer electrons from the molecule to the semiconductors. And we have done this for a number of material. So the doping process by direct doping, it's very efficient typically. However, the result is you start with a molecule where the LUMO level of ionization potential is very, very low. So the molecules are not very, very stable. So the most efficient way, the most practical way to do doping would be instead to use a different approach, which is used as a precursor type and doping, which consists instead to start with a precursor, which is converted into active species, and this active species that they can transfer the charge, the electron, from the molecule into your semiconductor. This process results in molecules which are more stable. The process is more controllable, but typically it's a very slow process and typically poorly efficient. There are many type of precursor type and dopants. These are some of is an example of class. And in this type of dopant, the doping species is associated to the cleavage of this carbon-hydrogen bond. And the bond get cleaved primarily heterolytically, so with formation of hydride. And then this hydride either add to the semiconductor, and then this added addition products then are the species which transfer the electron. They do the doping process. The mechanism can change considerably depending on the dopant, but also depending on the semiconductor. But no matter what, the process is not very, very efficient. So the question, can we make this process more efficient? And this is a work we just published, and I want to, first of all, I mean, I was involved, but the person who invented the process was Jugan Guo. He's the one who led the project. And the question we ask ourselves, can we actually make this process much more efficient by using a catalyst? Okay. And as I want to remind you, so the precursors has to be converted into active species, and it has to go through a transition state, which typically is high in energy. And the idea is, if we use a catalyst, we can reduce this activation energy and facilitate the process. So how did we do this? We did this as an example using this dopant. Again, we want to break this CH bond. As a catalyst, we use metal particles. We use many of them, and the one we studied the most is gold. And we use many different types of semiconductors. These are N-type semiconductors, polymers, and small molecules. And just let me show you one example. This is an example using this polymer and this type dopant. This is the reaction, has upon doping. So the starting material and the final products. And we monitor this reaction without any catalyst. The temperature of the process is about 20 degrees for 10 minutes if there is no any catalyst. If we do in the presence of catalyst, we kept the same temperature, but the process only is for 10 seconds. And you see here is that if you compare the two reactions, this is the UV visible of the film of the polymer for the doping reaction without catalyst. There is only a small doping, and you see here from this UV. Instead, if there is the catalyst in only 10 seconds at the same temperature, the reaction is very efficient. This is a EPR. That is without catalyst, the spin density is much lower. And this is the electrical conductivity when we compare the process for different, we change the molar ratio between the polymer and the dopant. This is not so important. No catalyst, the doping efficiency is very low. The conductivity is much low. In the presence of catalyst, with much less time, the doping efficiency is much larger, and the electrical conductivity, when you improve the doping content of about 40%, much, much larger compared to a catalyzed system. And the reaction is extremely fast. I don't know if this video is going to start, but let's see if it does. So this is an example of the blend solution. And here we put the solution in air on a glass slides where here there is no any catalyst. The catalyst deposited, you see the slight variation in color, are the nanoparticle. And here there is the nanoparticle, and you see the reaction occurs basically immediately at room temperature. So nominally, the reaction occurs at 120 degrees, but in practice, the reaction is extremely fast, very, very efficient, and it results in very large conductivities. We study using this reaction more deeply from the computational point of view by the work with Alessandro Motta, and we study the kinetics in collaboration with Simone Fabiano. This is the sort of the catalytic cycle, and the reaction as modeled by computation occurs by, again, breaking this bond heterolytically. So you have gold, then the hydride is transferred on the, I don't know why this is happening. The hydride is transferred on the gold, forming the hydride gold negatively charged surface. This surface can transfer one electron, so it dopes the molecule. And then this can happen another time to form the radical and ion. And then it can transfer a second electron to repristine the gold and then eliminate hydrogen. And we talk about activation energy. So we monitor the uncatalyzed process. The activation energy is on the order of 20 kilocal per mole. Instead of for the catalyzed process, which is monitored here in orange, the activation energy is on the order of 10 kilocal per mole. And this translates in a huge variation in terms of kinetics, so in speed, between the uncatalyzed process, which basically the reaction doesn't happen if you don't heat it, to the catalyzed process, which the reaction also happens at 25 degrees without any heating. So with this one, I conclude. I think I've been in perfect time. So I show you, mostly 4 types of results. One about the photolithographic patterning of organic semiconductors. We can use this blend approach to create pattern semiconductor islands, which are comparable with fab processes. We can enhance the plasticity molecular semiconductor by designing a proper additive to the molecular system, or for the polymer by introducing deconjugated units. I show you that porous semiconductor morphology for electrochemical transistors. This can be important if the polymers is very textured and or is hydrophobic. If you're using a polymer which is hydrophilic, is not that important. Also, I show you that we can combine organic and inorganic semiconductor to create efficient electrolyte gating. And finally, I show very briefly an example of using a catalyst to enhance the efficiency and the conductivity of n-doped organic semiconductors. And I acknowledge all the collaborators into the in each of the view graphs. This is a brief summary of some of the collaborators and some of the funding agency. And I thank you for your attention. Thank you.
Hi, and thanks for your wonderful talk. Now it's time for questions or comments. Can you hear me now?
I hear you, but not very loud.
Okay, now it's time for questions or comments. I think the audience maybe have some questions.
Okay, Anonia, yeah, it's okay. It's clear.
Yes, it is.
Okay, great. I have several questions. Yeah. The first question is about your photolithography for organic semiconductors. I found you show several images, and the resolution is seems several micrometer, around 5 micrometer or around that. Yeah. Yeah, it is possible to improve the resolution. Yes.
Yeah.
Yeah.
Very good question. We did it, 5 micron is sort of quite reliable in terms of line separation. We have been able to go down to about 1 microns for the DPP polymer. For the N2N200 polymer is closer more to 5 microns. The resolution strongly depends on the ratio, molar or weight ratio between the semiconducting polymers and the additive. So if we put more additive, the resolution can be improved more, but the field effect mobility decreases a little bit. So you need to have a balance between the, performance, field effect mobility or current, and the resolution you want to achieve. For most of the OTF, amorphous silicon TFT for conventional LCD and low resolution display, 5 micron is typically okay.
Okay, clear. It's actually this is the strategy for balance. I have the sixth question is about your plastic polymers. You just suggest the plastic polymer as a binder stabilize the green boundaries. Yeah.
Yes.
And I'm still I didn't catch the detailed mechanism how to stabilize the green boundaries by as a binder.
Very good question. Yeah, I went quite fast. The way what we are quite sure is the mechanism is because the polymer additive we are using has these end units. Okay, so the polymer at the end there is the two molecules attached, and you have a sort of a molecular recognition between the molecules of the semiconductor in red, and then you have your grain boundaries, and basically you have the polymers, which is somehow attached to the semiconductor on both sides. And so it's a sort of using this molecular unit attached to the polymers so that they recognize the semiconductor at the grain boundaries. And the proof is really this experiment. This experiment is we have this polymer with the end group, and if we bend it, there is no crack. Instead, if we blend the small molecule with N2N200, which does not have the red small molecule at the end, then you bend and it cracks. So really, this polymer really likes it's sort of molecular recognition mechanism. And we also made the polymers where the building block, this is very recent work, the blue component doesn't have to be N2N200. It can also be any polymer. It can also be an insulating polymer, as a matter of fact. You still get the same results in terms of plasticization.
Okay. And have you observed the stability of the green boundaries? For example, the the number of the ground boundaries and the size of the ground boundaries. Yeah, for a long time. Yeah.
Yeah, not for a really extremely long time. We did. We made transistors, and this is comparing. So here we bend the devices at 4 millimeter, and the black is for the film without the additive, and you see the mobility decreases, and then it continue to decrease. It never stops. Instead, if you add about 5% of the polymer here, the mobility decreases at the beginning, but then it stabilizes. Basically, it tells us that at the beginning you form some cracks. Probably you see here, right? There's a couple of points you can still see some crack. So at the beginning, the mobility also drops a little bit, but then after this crack form, the other grain boundaries are stabilized, and the performance do not change anymore. Yeah. So I think this is a quite good evidence combining this experiment with this experiment, particularly the control experiment. It tells you the importance of the molecular design of the binder. And this is a sort of final experiment, right? Because if we add N200, the mobility continue to decrease. So we don't plasticize the grain boundaries. You really have to have this polymer. This polymer is not good. This is good.
Yes. Thank you. The last question is is about the last part. The good nanoparticles are the catalyst for n-doping organic semiconductors. Yeah, and because gold usually is very stable. Yeah, as the catalyst for n-doping is really very interesting. Yeah, for the doping process, and is it possible to capture some intermediate states during the catalyst process? Yeah, it's possible.
For a second, it broke your. So if it's possible to
capture the intermediate states during
this species, you mean?
Okay, yeah.
If we can stop and yeah, we haven't been able to isolate, obviously not the transition state, but the intermediate species. What we know is we clearly see is that we did many type of experiments. I'm sorry, I don't have the view graphs ready, but what we know is from this reaction we form hydrogen, and we have a mass spec which it forms hydrogen first. Second, we know that we don't see any addition products. I don't know why this is happening. In a conventional doping process, the hydride, let me go back here, the hydride add to the polymer to form intermediate species. We don't see any of these hydride addition products. We don't see them. For the gold particle, they can be recycled. Basically, you can take this surface after we put the solution, we can wash it and we can reuse it. So there is a number of evidence that the catalysis occur. We couldn't isolate any of these intermediate product at this point. I guess it could be quite difficult to do that.
This doping mechanism is a supposed mechanism or approved mechanism?
Yeah, I mean, we have evidence of this mechanism. Obviously, if you take a catalyzed reaction means the starting point and the end point should be the same, right? with or without catalyst. This is so you form the same type of product with the catalyst or without catalyst. Second, the catalyst does not get consumed or reacted during the reaction. Third, the reaction is much faster. So these are the sort of the three key points of a catalytic process. And we have evidence that, the catalyst is recovered, the product are the same with or without catalyst, and the reaction is much, much faster compared with or without catalyst. If you look at the catalytic cycle, there is no any species which we can stop or quench the reaction to understand exactly what's going on, right? Because you only start from this molecule and you form the radical, you form the cation, and you start from the perilene molecule and you form the radical anion. So it is extremely difficult to, quench the reaction, or what is called trap intermediates to understand exactly what is the route, and whether there is very different routes. So it's going to be extremely challenging to trap actually species. I think this is a very reasonable mechanism, and it is, at least for this small molecule. For the polymers, we haven't done the whole study. I mean, maybe for the polymers, there could be other ways to the reaction can happen. We haven't modeled yet for the polymer, but this seems quite a reasonable process.
Yes, it's very difficult. But with the single electron transfer, and it will form some radicals. And is it possible to capture this radical information by EPR or other method?
Yeah, I mean, it's we did a quenching reaction during and what we can only see is the small molecule. So it means there is no any hydride addition. There is no any other species that we don't see in this type of catalytic modeling of the process. So we quench the reaction with water, we quench the reaction in air. We see the same type of reagents. We can trap this radical, for example, by I think this could be an experiment where we can just take the nanoparticle and this molecule and put it together and see if we can trap the radical cation. This is actually, it's not the radical, this is the cation. And we see the cation by UV, because the UV, from UV visible, you can see this cation quite well. I don't know if we see it here. This is the photon energy. It is more here. It is more shifted. So you don't see it here.
Okay, it's clear. Thank you very much, Antonio. Thank you for your excellent talk.
Thank you.
Any more questions?
Hello, Professor. You hear me?
Yes, I can.
Okay, thank you for your talk. It's very exciting and inspiring. I have two questions. The first one is about the photolithography work.
Yeah.
Yeah, and I noticed that you use the SU8 as a crosslinker, and it works very well in the N-type semiconductor. For the DPP type, there's a little bit of hysteresis, right?
Yes. This is
so why is that?
Yeah, this is something I really don't understand. to be really frank. I would expect, for those of you who are organic chemists, the way SUE cross-link is by opening these rings, right? And you form OH groups. And so you would expect for an N-type to be an issue, right? Instead of for a P-type should be less of an issue. We don't see that.
That's the point. Yeah.
It's
interesting phenomenon that I think maybe there, for example, if you want to initiate the photocurable reaction, maybe you added the photo acid to be the initiator, right? Or how do you?
We don't want to. We don't. Yeah.
So maybe the acid or other species may dope the DPP polymer or behave as a trap, so there will lead to the hysteresis. Maybe I don't know. So, but I think it's a very interesting phenomenon. Maybe, will lead new knowledges.
Yeah, I totally agree with you. It's something I don't fully understand, but this is what the experiment, and I didn't believe it, so I asked Bingao to redo this experiment, and he did it several times, and we always see hysteresis for the DPP, and independently also if we use the cellulose, both.
Okay.
I mean, I think a lot of depends on this, you know, because you don't get a uniform film on the cross section. There is a sort of a phase separation. There is a very complex morphology which involves nanofibers. So probably depending on how this phase separation happens, then will translate into, you know, this variation in the electrical performance.
Yeah, maybe you're right. The morphology or the phase separation maybe affect the interface between the semiconductor and the dielectric layer. That may also lead to the hysteresis. Maybe, but it's very complex. But anyway, it's a very talented work. And my second question is about the electrolyte gated, the OECT. Yeah, the PNAS paper.
Electrolygated, sorry. This one?
Yeah, this one. And I noticed that you use this as a amplifier for the EOG, right?
Yes.
So is the device solid state or liquid state? Because did you integrate the device with the skin or not?
No, not at all. Only the pads which are commercially available are touching the skin. Everything is outside. Yeah, there is the scheme into the paper. I'm sorry, I didn't have, if you want to touch the device to the skin, you have to go through a process that is very complex. In the US.
That's right.
You need all authorization. It takes forever. So no, it's not integrated to the skin. Only 3M pads are touching the skin, and then everything is wired.
Okay,
maybe someone has to explain me why this is moving. I don't know. There is something in transitioning the view graphs. I apologize.
Okay. Thank you so much. Thank you. Very wonderful talk. Thank you.
Hi, Anony. Can you hear me?
Yes.
This is Li Qiang speaking. I have two questions. The first question is about the N-type doping. You develop a high efficient N-doping method, but I'm curious about the mobility. In my opinion, maybe the molecular dopants may penetrate into the lattice of the organic semiconductor crystal. So the mobility may be decreased. Is that true?
It depends on the polymer. We did, there is a lot of, in the paper there is a supplementary information which is like 5 papers, and we model and we know what are the field effect mobility for these semiconductors, and then knowing that and assuming how it could change with the carrier density, you can estimate, from the conductivity, you can estimate the carrier density. But the answer is it depends on the polymers. For some polymers, for example, for N2N200, we saw a typical quite dramatic decrease of the field effect mobility when you have a lot of dopants, and this is typical for this polymer. For others, with the doping, the field effect mobility increases, and then it remains roughly in the same range. So it really depends on the polymer. This is at the very high level, my answer.
Okay, thank you. Then is the doping process is reversible? I mean, can you dedope can you reverse the n-type doping process?
Yeah, it is reversible. So if you take the color polymer, and then for example you take this and this polymer doped and you re-expose it to the air after, it depends on the polymer and the thickness of the film, but after certain amount of time you can dedope it. For the small molecule, we also, like this, after the process is complete, you can take the glass and dissolve it. The nanoparticles are attached to the glass, so they don't move, they don't get removed. So you can take the film and dissolve it, and you can re-see again. You can do a TLC, you see the small molecule. You can do mass spec, you can do NMR, you see the starting material.
Okay, it's excellent work. My second question is about the deconjugation method. How to control the deconjugation degree?
Yeah, the reaction is done by still a polycondensation reaction. So we use a dibromide of this material, and we use a distannylated of these two building blocks. And this is the work we have published a few years ago. The kinetics, the rate by which these two monomers react are identical. So basically, you mix in a certain ratio these two, and you end up with a polymer which incorporates the unit in a certain ratio. So it's a random copolymer incorporating the quantity of the red and the blue components.
Okay, thank you. I got it. Any more questions? Okay, wait a minute.
Hello, Anthony. Do you hear me?
Yes, okay, I can.
I have 3 questions. Can you back to the slides of the flexible device on the needle?
A flexible, yeah. Which one was that? This one?
No. Yeah, this one. I noticed the finger B. So the first line is on the glass and the second is peel off. So when you test it, you just on the glass and then peel off for 2,000 times?
No, this is bended. It's bending. Then get bended at a 1 millimeter radius.
Oh, you just bend it, right?
Yeah.
Okay. So how you test the device on the needle? My question.
Frankly, I'm honest. I don't know. This was done by the group of Someya. So I'm frank. To be honest, I don't know how they measure it. I don't know if they. He's obviously a super expert of flexible electronics on very soft substrate. I assume they have probably a machine where they can bend it. bending it multiple times, because you see there is 5,000 times, but there is the device are tested only 1, 2, 3, 4, 5, 6 times, right? So I assume there is a little machine which roll it, unroll it, and then they stop it, they measure, they put it back. This is what I believe what they've done, but
okay.
I cannot.
Okay.
Yeah.
So
You can ask me now.
Okay. Can you go to the slides of the circuits? So you make the circuits, right?
The electrolygated.
Yeah, the electrolytes circuit.
Okay. No. Yeah, this one.
This one. Yeah, this one. So I noticed the gain of the inventors is very high, but the oscillator, the frequency of the oscillator is very long. So can you explain it? Yeah, the
Yeah,
H,
I mean,
finger H.
yeah.
But the gain, the finger E, I noticed the gain is very high for the inventor, but the finger H frequency is very long. So
figure H. You mean the
I mean the frequency. The frequency is very long, right?
Yeah,
so
yeah. I mean,
can you get high frequency?
These are electrochemistry. So I mean, the ions have to intercalate into the polymer. So it's not like simply an electronic process. You have ion motion, and this is what for electrolyte gated circuits. So you have a very large amplification, but the speed is it's low.
Okay, so you mean that when we use the electrolytes dielectrode, we can't get high frequency, right?
Exactly.
Okay. Yeah, thank you.
Any more questions? It seems there's no more questions, Anthony. So maybe we can stop your talk right now.
Okay.
Thank you very much.
Thank you again. Good to see you guys.
Hope to see you in the future in China.
Yeah. I really want to get back to see you guys.
Okay, bye.
Thank you. Bye.
Bye.
Bye.